Okay, so we're going to talk about first some parent functions and transformations. Now, luckily, you already have looked at your parent functions from your summer packet. I will give you a parent function chart that you will need to fill out by Thursday of all the parent functions that we know, and what we know about their domain and range and intercepts and that kind of thing. So I'll hand that out at the end. Now, you have not seen this function before, have you? What does it look like? It looks like stairs or steps, okay? We call it the step function, okay? This is how it's notated, right here. It's called the greatest integer function, all right? We nickname it the step function because it looks like a set of stairs, okay? Okay. So this is the notation. When we say greatest integer, we say the greatest integer less than or equal to x. Okay? What does that mean? All right. If I say, what is the greatest integer of 1/2? Integer, we're talking about 1, 2, 3, 4, -1, -2, -3. Okay, you know what integers are. What is the integer that is less than this? What would this bump down to? What? 0. Okay, you're going to kind of think if it's not an integer, we're going to bump it down to whatever integer is below it. All right, so if I gave you 7.5, it would bump down to be 7. But what if I gave you the greatest integer of 7? It's going to stay as that number. Okay. No, it's always going to round down. Okay, great. Yeah. We're always going to round down. Okay. So, let's try it. Greatest integer of -1.5. What? Oh, good. We're bumping them down, right? We round down to the lowest. Okay. Greatest integer of 3. 3. Okay. Now that you know what it is, let's talk about why the graph looks the way that it does. Okay? Anything I plug between 0 and 1 into the greatest integer function. If I plug in 1/2, it gets bumped down to 0. If I plug in 3/4, it gets bumped down to 0. If I plug in 0.9999, it gets bumped down to 0. So this little horizontal line is representing all of those numbers getting bumped down up until, 1.99999, or sorry, 0.99999 is still getting bumped down. But then at 1, we get to keep it at 1. All right, so we have an open circle because anything up until 1 is going to get bumped down to 0. But then at 1, we get a bump up here to 1. And anything between 1 and 2 rounds to 1. Okay, so we have a closed circle at the beginning and then an open circle at the end of the step. Okay, does that make sense? Okay, now you'll notice that this is still a function because it passes the vertical line test because I'm only going through one actual value. Okay, that open circle is in a coordinate. All right. Now, when you plug in to a function that has the greatest integer in it, please evaluate that before moving on for example, if I ask you to evaluate this f of 3/2, okay, that means I'm going to plug 3/2 into here. Just like an absolute value, you need to evaluate the greatest integer function first before you can multiply it by 2, okay? Kind of like our parentheses rule. So what is the greatest integer of 3/2? 1. So this is 2 times 1, which is 2. Do not distribute that 2 into that notation, okay? So just be careful with your order of operations. Okay. Piecewise functions you've done before. You've graphed them in Algebra 2, okay? So this next slide is going to be review. I'm going to tell you how I want you to graph them, okay? They're the easiest thing to graph. You really don't have to think too hard about it, okay? So when I say a piecewise function, what does that mean? Listen to what it is, a piecewise function. Do you think it has something to do with pieces? Maybe. Okay. A piecewise function, okay, is a set of functions. So it's pieces from multiple functions that cover a specific part of the domain. Maybe all real numbers, maybe just a chunk. Okay, but we're going to put 2 or more functions together, but only pieces of them so that it remains a function. Okay, so you may see like half of a parabola and half of a line. Okay, you may remember graphing something like that last year. Maybe. So what we are going to do is we are going to look at how they're defined. This is what they're going to look like, okay? More than one function, but where the domain is specific, okay? We've all seen something like this before, correct? Okay. So this is saying our function is 2x plus 3 when our domain is bigger than or equal to x. Our function is negative x plus 4 when our domain is anything above 1. Now, what kind of function is 2x plus 3? Oh, it's linear. Negative x plus 4? Linear. Okay, so we have pieces of 2 different lines. Okay? Whether we know how to graph lines or not, we can graph this. Okay? Because all we're going to do is make a table. Okay? Anytime you have a piecewise function, I want a table of values for each piece. Okay, so let's look at our first piece. 2x plus 3. Okay, now it says our domain begins at 1. So that's what I'm going to plug in first. Does our domain include 1? Yes, so I'm going to make a note to myself that this needs to be a closed circle because it does include 1. And then I'm just going to have you pick, okay, this x is less than or equal to 1, and so we need to get smaller with our domain. So those are the numbers I'm going to plug in. When I plug in 1 to 2x plus 3, what do we get? When I plug in 0, and I plug in negative 1. 1. So I'm going to plot those points. 1, 1, 5 is a closed circle because we do include 1. We have 0, 3, and negative 1, 1. So we began our domain at 1, and we have everything less than or equal to 1. So there is that piece of our function. Our second piece is negative x plus 4. Where does its domain begin? It says greater than 1. So what we're going to do is we are going to begin at 1, but does it include 1? No. So we are going to, I'm going to make a note to myself that this coordinate has to have an open circle. Okay, because it's anything greater than 1. So we're going to start at 1, but having an open circle so it's not included. All right? And then our domain gets bigger than 1. So I'm going to pick values bigger than 1. Okay? When I plug in 1 to negative x plus 4, we get
3.
When I plug in 2, okay. So I have 1, 3, 2, 2, 3, 1. Okay, everything else is included, so we make closed circles for the rest of it. So we begin our domain at 1 and we get bigger. So I'm just going to connect those dots to make my line. Okay. So there's our piecewise function. We have pieces of 2 different lines. Notice how it's still a function because it's still going to pass the vertical line test. Okay. Now, it is possible that for these 2 coordinates to overlap, if I would have gotten the same coordinate here as I did here, that's okay, because then the open circle and the closed circle would just form 1 coordinate. So if that happens on your homework, that is okay. Okay, it is possible, like if it looks something like this, where the open circle and the closed circle overlap, that is okay. Okay. Do you remember graphing these now? Yes.
So then for that, would you just like draw a closed circle and then write it out there or something?
Well, what I would do, I would draw the open circle, and then I would color it in for the closed circle. Okay? If you draw a circle around it, it's not a big deal, but you don't have to notate it any different. Okay? All right. I promised you that we would talk about transformations again, didn't I? Here it is. Okay? So let's see what you remember from your summer homework. If I want to shift C units up, okay, so we're going to have a function. How do I shift up? Yes, we add C to the end of our function. What if I want to shift down? We subtract it from the end of our function. Okay, notice how up and down that deals with the y values. So it is outside of our function. It's after our function. That is how the y values get affected. It's supposed to be minus. Thank you. Thank you for paying attention. Sometimes when I talk, I write something that I say. All right. How about to the right? Subtract C where?
From the inside of the function.
From the inside. Okay, anything that we are going to do that affects the x values has to be inside of our function. Okay, so if I'm going to go to the right, first of all, it's inside and it's backwards from what we want to think. It's actually minus C. To move it to the left, we're going to have that plus C inside. Okay. Our reflections. If we want to reflect about the x-axis, Okay, let's think about what that's going to affect. Here's my x. Here's my y-axis. If I'm flipping my x-axis. If I'm going to flip something over my x-axis, what values are being affected, the x or y? The y values. So that's why our negative goes on the outside. Now if I'm going to flip something about my y-axis, what values get affected? The x values. So your negative goes inside. Okay. Let's add a couple more. Is everyone okay here? This is all review, right? Here's something new, what we call non-rigid transformations. They're going to, okay, shifts and reflections are rigid because the shape doesn't change. We just move it or flip it upside down, okay? When I talk about a non-rigid transformation, the shape is going to look different. Okay, basically these are going to be called stretches and shrinks. Okay. So we're going to talk about first a vertical stretch or shrink. When I say the word vertical, what do you think of? X or Y values? Y values. Okay. So we're going to have something outside of our function. Okay. Here's our vertical stretch and our vertical shrink. Okay. Notice for both of these we're multiplying by a C value on the outside. All right. If C is bigger than 1, then we have a stretch. We're stretching it vertically. Okay, so we're making it taller almost. If our C is between 0 and 1, then we're shrinking it vertically. We're going to squish it vertically, make it fatter. All right. So how are we going to apply these? How are we going to make our new graph look? Okay. Since this is just affecting our y value, we're going to take our y value, and all we're going to do is multiply by c. So whatever our original y value is, we're going to multiply it by our c value, and that's our new y value for our stretch or our shrink. Now, we have a horizontal stretch and a horizontal shrink. These are backwards from our vertical stretches and shrink. They affect them the same way, but backwards, okay? First of all, if we talk horizontal, we're talking about affecting the x values. So our c is now going to be inside of our function, okay? So our horizontal stretch and shrink, our c value was multiplied inside. But notice how our stretch is when c is between 0 and 1, and our shrink is when c is bigger than 1. Okay, so those get flipped. Also, anytime we put something inside of our function, it always acts backwards. When we want to shift right, we subtract c, which is backwards, right? So to get our new x value, we're going to multiply by the reciprocal of c to get our new x value, since everything's backwards inside. So we're going to go through, I'm going to give you a little graph, and we're going to go through different transformations from both this page and last page with this graph. How do you take this chunk and apply the transformations to it? Okay? So you can write down this graph and do it every time, or you can watch, that's up to you. Okay? Any questions? Okay. So here we go. This is f of x. I want f of x plus 2. What is this plus 2 doing? Okay, we're moving up 2, right? So I'm going to take each coordinate and I'm going to move it up 2. Done. Here's f of x. I want f of x minus 2. How does this affect my graph? Move it right 2. So I'm going to take each of my coordinates and I'm going to move them right 2. Easy enough? Okay. How about this one? What kind of transformation is this? It's a vertical stretch. First of all, it's on the outside, so it's vertical, right? Since this value is bigger than 1, it is a stretch. How do we apply this stretch?
We multiply all the values by 2.
Which values?
The y.
The y values. Since this is vertical, we only worry about the y values, and we multiply all of our y values by 2. So this is the coordinate 0, 1, right? What's our y value multiplied? So negative 1. What's our y value multiplied by 2? So this stays at 0 and then negative 2. This coordinate is 1, 0. What does it become? 1, 0, because 0 times 2 is 0. This coordinate is 3, 1. What does it become? 3, 2. This coordinate is 4, 2. What does it become? 4, 4. Okay. Let's do this one right here. Okay, I don't think we need to do all of my examples because I think we've done transformations before. Let's look at this one. F of negative x. Reflect about the y-axis. Okay, so the y-axis is just a mirror. Since this is on the y-axis, it stays. This guy, we reflect over to here. This guy, we reflect over to here. And this guy, over to here. Can you handle that? All right. Last kind of problems you will encounter will be, well, we might want to do this one. What is this if it's on the inside? Horizontal. In this case, it's shrink. So we would take our, well, is it a shrink? It's a stretch. We would take our x values, and what would we multiply them by? Which is 2. Okay? So, in all of our x values, we multiply by 2, just like we did with our vertical stretch. Okay? This is the kind of problem you will see in your book. Look, this is from your book. All right? Now, I don't always like the constant coming first. If this were me, I would rearrange it to this. Okay? If you want to open your books, you can, because there's multiple parts of this problem. Look, I don't have any instructions up here. Okay? The first set of instructions is to say what the parent function is. Okay? What is the parent function of this graph? X squared. So our parent function we're going to name as f is x squared. The second part is to verbalize those transformations. Okay? So first of all, what is this negative doing? A reflection about what? About what? About the y-axis? Do you agree? Is it on the inside or outside? Negative. From the outside, isn't it? So it's a reflection over the x-axis. Because it's affecting the y values. All right. This plus 12. What? Okay, we're going to shift up 12. So we know x squared, we know that's a parabola, right? You don't have to be super exact here. All right, I'm going to go ahead and, I think I have enough room. Okay, so we're going to shift, we're going to reflect our parabola upside down, and then we're going to shift it up 12. Okay, there's your graph. You don't have to be super exact. Okay? But you at least know those 3 points, right? You know, we have the 0, 0, the 1, 1, the negative 1, 1. So we know that there's those triangle points, right? Okay, so there's part C. Now part D, like in your summer packet, is to write this. We're going to write g of x in terms of f of x. So instead of negative x squared plus 12, we're going to write negative f of x plus 12. Okay, so instead of the negative x squared, we're going to write it as f of x, since they are one and the same. Okay. Is everyone okay with that? Okay. Okay. Good. So it's it's just like the problems in your summer packet. Okay. This is your homework. This 8 basic function chart needs to be filled out by Thursday. Okay, it doesn't need to be filled out right now. I will get an answer key online, but not today, because I want you to kind of work on it your own by yourself for a little bit. Okay, so on this 8 basic functions, you're going to have to give me the graph, the equation, the domain and range, the intercepts, both x and y, and then you're going to tell me if it's even, odd, or neither. Okay? Just look at the graph and tell me. You don't have to prove those. Okay? All right, I'm going to give you back your summer quiz. Now, this will never ever happen again, so take advantage of it. The beginning of the year, you just came off summer vacation. Some of you are still trying to get back into the school mode. This probably wasn't your best quiz in the entire world. That's okay, I understand that. What I'm going to allow you to do is make corrections for half points back. Separate sheet of paper. Redo the entire problem if you want those half points back. Legibly, please. Don't just give me the answer. Don't do half of it. Even if you miss one little thing, you have to redo everything. Okay? So help me out. I'm still learning your names. You know? Jonathan. Chase. Emma. Emmy. Okay, Rachel. Miranda. Rebecca. Emily P. Joey. Josh. Sean. Noah Ed. Paige. Ty. Jared. Dakota. Noah. Casey. Morgan. Okay. A couple of things. Standard form. The AX plus BY equals C. A needs to be positive. A and B need to be integers. You can put it into Y equals MX plus B form and then rearrange things and multiply until you get to here. A needs to be positive, and B need to be integers. If I took off a half point on one of your graphs, it's because you were close, but not close enough. On number 3, I need to see that you know what the y-intercept is and the slope. You can't just draw a line, okay? Give me some coordinates at least, okay? On the back side, number 9, please be careful. First of all, do you see any equal signs? Do you see any equal signs on 9 or 10? Then don't solve. Okay? Number 9, give me an algebraic expression or a value. Okay, B and C are just numbers. Number 10, it says factor. Factor. Do not solve, just factor. Okay? Part C, if I wrote careful, remember when you subtract a function? When you subtract a function, you are subtracting the entire function. So please be careful with your negative sign. I'm giving you hints here. These are common mistakes. Okay? I'm giving you until Wednesday to give me corrections on these. I know you have homework tonight, you have homework tomorrow. I'm going to give you 2 days. Wednesday, if you want to turn them in tomorrow, great. Okay? This is the only time you will ever get quiz corrections. I don't care if you got a 29 out of 30. Do the correction, and then you'll have 29 and a half out of 30. Okay? Okay? If you got 20 out of 30, you can raise it to 25 out of 30. That's not. Okay? Please use these corrections.
I like this idea.
Okay, use
We
it.
should adopt this like later on down the road.
No, I'm only nice once. Only once. Okay, I like to do one quiz recording. So this is like freebie. Right?
That's true. We do like 2.
Oh, and I recorded all of that, didn't I? Awesome.